Okay, yt is the dependent variable, what we are trying to explain. The xt's are our independent variables. Or we can think about these as the explanatory variables. The variables that we think explains y. So x's are what we think explains y. What are the betas here? The betas are the marginal impact of x on y. So how much does x impact y? That's what beta is. So if we look here, for instance, beta 1 is the marginal impact of x1 on y. Right? So one way you could think about what beta 1 is it's the change in y from a change in x1 holding everything else constant. So holding everything else constant and just changing x1, how much will y change? That's what beta 1 captures. And then finally, alpha is just an intercept or a constant. And what's UT? Random error. No econometric model is going to explain everything. Right? No econometric model is going to explain everything. So this is how most econometric models are set up, right? And so if you think about what this model is saying, it is saying that we have an x, right? Let's call this x1, and we have y. And if we plot the data might look something like this, depending on what x and y is. What we really have done here is try to fit a line that best fits the data, right? What an econometric model is doing is it's basically trying to figure out what line best fits the data. So in other words, what's the best alpha and the best beta that fit the data? And we'll talk about what we mean here by fit in a second. So let me give you an example here of an econometric model related to growth, right? This is from a paper by Dollar and Cray. And actually, let me back up here. Their question for their paper is economic growth good for the poor? That's their question. And so they develop an economic model. And here's the model. They use as their dependent variable the income of the poorest 20%. And their explanatory variable is overall per capita GDP. So what they're interested in is, does having high per capita GDP also lead to high growth of the poorest 20%? Okay? They actually, when they do the model, they actually do this. They actually use the data in logs. And this is something that you will see quite commonly in many of your papers. What's the advantage of putting the data in logs? That beta then can be, I shouldn't say expressed, I should really say interpreted as a percent. So that's their model. They look, this model is in log, what we call log form. The data is in logs, where they look at the log of the income of the poorest 20% and the log of per capita GDP. So to just look at the actual data here, if you want to see what their results look like, my sharing is not really working here. There we go. Okay, so here's an actual figure from their table. Is growth good for the poor? So what they have here on the vertical axis is Y, and on the horizontal axis is X. So the vertical axis is the log and per capita income of the poorest 20%, and the horizontal axis is per capita income. And then they fit a line to this. So there's the data. You can see all the plots. And then when you fit the line, what do you see about that, the slope of that line? It's positive, meaning that there is a positive relationship between per capita growth and growth of the poorest 20%. In fact, if you look at the data here, what do they actually find? They have this kind of reported in a weird way. They have Y is equal to 1.185 times X minus 0.0068. So that minus is the constant, and beta is 1.185. Okay, so how do we interpret that? Beta here, we're going to call this beta hat, meaning our estimate is 1.185. What does that mean? The way you interpret that is a 1% change in per capita GDP, or X, leads to a 1.185% change in income of the poorest 20%, which is Y. That's how you would interpret that coefficient. Why it changes? Because it's the data is written in logs. So then you can interpret it as a percent. So that's what an econometric model is you're basically trying to fit a line to the data, a line that tells you the best impact, or the best estimate of the impact of X on Y, your explanatory variable on your dependent variable. Now, the next question here is, how do we estimate alpha and beta to get what we're going to call alpha hat and beta hat? Putting a hat in this context means our estimates of alpha and beta. How exactly do we do that? And this is where ordinary least squares comes into mind, or comes into play. Okay, ordinary least squares, or often referred to as OLS. What does ordinary least squares do? Ordinary least squares chooses alpha hat and beta hat to minimize the sum of squared errors. In other words, it picks the best alpha hat and beta hat. For those of you who've taken calculus, this notation might look familiar. It picks the alpha hat and beta hat to minimize the sum of the squared errors. Or, what are the squared errors? That. It's minimizing the sum of the squared errors. So what it's trying to do is it's trying to figure out what the errors are, squares them, and then picks the alpha and beta hat that minimizes the summation of all those squared errors. Right? Why does OLS use squared errors? Anybody know? Why do we pick I mean, minimizing the sum of errors probably makes sense, right? Because we want to use all of the error. Why do we minimize the sum of squared errors, though? What's the advantage of that? Can you help me out? Yeah, Chase. Why do you square the errors?
It helps us not accidentally like overshoot to one direction or the other, because errors could be positive or negative. But when we square it, it's automatically going to be positive.
Right. One advantage is it makes all errors positive. So in other words, we don't have to worry about a negative error canceling out a positive error. Right? It makes all the errors positive, and so that's why we can minimize all the errors. Also, when you square the errors, what kind of errors are going to get weighted more heavily? Large errors or small errors? Large errors, right? When you square them, you're essentially making large errors larger. So to minimize that, that means it's essentially going to put more weight on minimizing large errors, right? So it minimizes, let's say it's another way. Ordinary least squares is much more likely to accept a lot of small error as opposed to a few big errors, right? It puts a lot of weight on avoiding large errors. So if I can switch back to this figure from our Dollar and Cray article, the black dots here are all the data points. And so what's this line doing? This line is minimizing the sum of the errors. So the error is the difference between the dot and the line, right? The error is the difference between the dot and the line. And so what ordinary least squares does is it takes all those errors, squares them, adds them up, and then figures out what's the best alpha and beta to minimize those sum of squared errors. Okay? So what this approach does is it tends to put a lot of weight on very big errors. Now you'll notice there are still some big errors in here, right? There are still some big errors. But in general, this is trying to pick the line that minimizes those big errors. How does it go about doing this? Well, this is really a calculus problem, right? Minimizing this equation that I showed up here a minute ago is a calculus problem. And basically what you have to do then is there's a solution to this. And what you then do with the solution is you use data to figure out what the numerical value of that solution is. If we were doing this by hand, it would be a pain in the butt. That's why we have computers, right? So nowadays, one of the dangerous things about ordinary least squares is it's so easy to do that a lot of people don't even understand what they're doing, right? You can take any data from that's in Excel and go up to the top, and under tools, you can do regression analysis. Tell us which variables is the dependent variable, which variable is the explanatory variable. Excel will crank this out for you in 2 minutes. People do this all the time, but they don't really know what they're doing, right? They don't really know exactly what ordinary least squares is attempting to do. Now, the question for us, and this will also be a question for many of the authors of the studies you look at, is they're saying do here, I should say, are our OLS estimates the best? In other words, when can we be confident that our ordinary least squares estimates are good? And when do we have to worry that they're not so good? Well, let's talk about that. What do we mean best? Well, econometricians say that to be best, an estimator must be a blue estimator. What do we mean by blue? Best, linear, unbiased estimator, right? B-L-U-E. So when we talk about best, what we're really saying is that it's the best linear unbiased estimator. And alpha hat and beta hat are blue, meaning they're best if two conditions hold. If they're unbiased. In other words, if the expected value of our estimator is equal to the true coefficient. So if our estimate of beta hat is equal to the actual beta hat on average, then it's unbiased. Okay. Another way of saying this is that there's no systematic error. Or predictable error. That might be a better, more intuitive way of thinking about unbiased. So does unbiased mean that our estimates are never wrong? No. No, we know they can be wrong. What we're saying is they're not predictably wrong. They don't predictably overestimate, or they don't predictably underestimate, or they don't make an error that could be easily correctable, right? That's another way of saying what unbiased means. There's no error here that's easily correctable. The second thing that needs to be true if your estimators are blue is that they have to be efficient. And what does efficient mean? They have the smallest variance that is possible. They have the smallest variance that's possible. To say this in another way, when our estimates are wrong, they're not wrong by very much. Okay, that's another way of saying the same thing. To say you have the smallest variance means that when you're wrong, you're not extremely wrong. You're just a little wrong, okay? So, you know, given we just been through election season, which would you prefer to look at? A poll that has a variance of plus or minus 1%, or a poll that has a plus and minus of 50%? Well, it's obvious, right? A poll that has a plus and minus of 50% can tell you nothing. The variance is so big that there's you know, it tells you nothing. None of the information that it tells you we can rely upon because there's just too much leeway for being wrong. Well, the same with ordinary least squares. We would like our estimators to have a very small variance, meaning that if they're wrong, they're not wrong by very much. So these are the two properties that we look for in our estimators, that they're blue. And to be blue means they have to be unbiased and efficient. Now, this, of course, is a discussion for a whole long, you know, whole block, right? If any of you take econometrics, or trying to look at, none of you have taken econometrics with me, I don't believe, no. So if you take econometrics, this is being offered second block next year, you know, a lot of what econometrics is about is actually investigating these conditions under which ordinary least squares works well. And if it doesn't work well, what can you do to make it work well, right? That's really what being an econometrician is about figuring out if your estimates are good, and if they're not good, how can I make them good? So it's a little bit beyond the scope of our simple review here to talk about all the things that can be a problem with your ordinary least squares estimators. But I do want to talk about common problems, particularly with an eye on the kind of literature that we're going to be looking at. Common problems that prevent our ordinary least squares estimators from being blue. Ah, damn, sorry. Okay, common problems that prevent our ordinary least squares estimates from being blue. 1, a particular problem in growth data is what we call simultaneity bias. What's simultaneity bias? Well, it's when X causes Y, but Y also causes X. Okay? The problem then, you can't separate the effects of one on the other. Okay, we talked about an example just yesterday, but there are many, many examples in the growth literature of when you have questions about simultaneity bias. Yesterday, we talked about education and whether more education leads to more growth. Does more education lead to growth? Maybe, but here's the problem. Does more growth lead to more education? That could also be true, right? More growth could lead to higher standards of living. What are people going to do with that money? They might spend some of it on education. So this is the classic example of education causes growth, but growth causes education. If you just try to do a simple model where you have education as the explanatory variable and growth as the dependent variable, you are going to have simultaneity bias and you cannot trust the results. Okay? What do? Well, there are solutions. And in fact, one of the solutions we're going to talk about next week is what's called an instrumental variable. And an instrumental variable is when you use something that is correlated with X, but not caused by Y. That probably doesn't make a lot of sense. Let me give you an example here. As I said, we're going to talk about an excellent example of an author who uses an instrumental variable next week when we talk about this paper by Acemoglu, Robinson and Johnson. So I'm not going to get into that paper today, but let me talk about another example. This is not an example from the growth literature, but it's interesting nonetheless. A study looking at the effects of guns on crime. And so what happens if you estimate this model? You have simultaneity bias, right? Could more guns or less guns cause crime? Yes, guns could impact crime. But is it also true that crime impacts the number of guns? Yes, you have simultaneity bias. Okay? So, what do? What do you do? Well, what if I could find something that's highly correlated with guns, but is not caused by crime? What if I could find something that is highly correlated with guns, but not caused by crime? So that's what an instrumental variable is. And in one study, they came up with a very clever instrumental variable. Gun magazine sales. And here I don't mean the magazines that hold bullets. I mean the actual magazines, right, that you read, right? So this is actually a very clever instrumental variable. Why? Because what's true about people who buy gun magazines? they also own guns. There is a high correlation between gun magazine sales and the number of guns. But does crime cause people to buy more gun magazines? That doesn't really make a lot of sense, right? So it's kind of it's a very clever instrumental variable, something that's correlated with guns, but is not caused by crime. So what you do is you use this as a replacement for guns. You go out and you estimate this. And if you do that, what do you find? That beta hat is greater than 0, meaning more guns cause more crime. There are other ways to control for this too, right? And you know, it's not really worth my time to go through all of the ways that you can control for instrumental variables or to control for simultaneity bias. And I don't expect you to know all of these. But in your papers, you are likely to hear your authors talk about simultaneity bias. And so you should know why they're talking about it, right? Because they're worried that their estimates are not going to be good if they don't think of a way of trying to control for the effect of simultaneity bias. Here's a second problem. Time series data with trends. If your data all has trends, it's going to tend to magnify the size of the correlation. In other words, it's going to make beta hats look large, right? So for instance, if I look at the correlation between population and per capita GDP, what am I going to see? Well, let's do this, a log of each of these. I'm going to see, let's call this per capita GDP, and I'm going to see population. And it looks like there's a really strong correlation between the two, right? If I calculate the correlation, correlation coefficient, it's going to be high, close to 1. The problem is, some of this is driven by the fact that they both have trend in them. So that's going to make the correlation appear bigger than it should. Okay. Likewise, I could have a different graph here. Let's say that this is the number of Justin Bieber albums sold. That's also going to have a positive trend and tend to go up over time. So what happens if I calculate the correlation between the number of Justin Bieber albums sold and population growth? I could find a positive correlation there. I could say, hey, Justin Bieber is causing a population boom. But that's stupid, right? It's appearance of a correlation because they both have trend. So the key here is that we need to think about detrended data. How, I mean, there's a number of ways. You could look at the change in X and the change in Y. And many of your variables will do this. Instead of looking at how X causes Y, they'll look at how the change in X causes the change in Y. right? That's a very common way of detrending. Or there's other technical ways of remembering this, of doing this, right? Max is, because he just took an intermediate macro, probably has nightmares waking up in the middle of the night, remembering all that detrending stuff we talked about, right? And those of you who took intermediate, we talked a lot about how you can detrend the data. I don't want to go back into all that again, other than to say you can detrend data, and that's what you should do. If you have time series data, you should detrend it first, right? You should detrend it first. Then you're going to get closer to real relationships. And so that's something that almost all of your authors are going to talk about. If they have time series data with trend, they're going to use detrended data. Also, I should mention here, another way that you can reduce trend is put your data in logs. That also helps remove some trend. And so you'll also see that a lot of your papers are going to put their data in logs, because that can remove some of the trend from your data. Okay, the third problem that we have to worry about, I mean, there's a lot of problems, but the third and the last one that I'm going to talk about here this morning is just having omitted variables. What happens if we are missing important explanatory variables? Right? What if we miss important explanatory variables? The problem is that the x's we include will pick up some of the effect of the variables we omitted. This biases our beta hats. Because the variables that we do include in the model, we're not getting the right estimates, because they're also picking up some of the effects of the variables that we didn't include in our model. So, you know, example that I always think of is, I saw this article in the newspaper, empirical study that says hot dogs cause cancer. And the study basically looked at cancer rates. Hot dogs eaten. And they found the beta hat's greater than 0. Hot dogs cause cancer. No. And I'm not buying that at all. Why? Because there's a lot of omitted variables in this, right? There are a lot of omitted variables. And some of them are highly correlated with hot dogs eaten. For instance, I don't know this for a fact, but I'm going to guess that living under high power electrical lines, people who live under high power electrical lines probably eat more hot dogs. And I'm betting that because there's another omitted variable, which is poverty, right? That probably the people who eat the most hot dogs are people who are also poor. If you're also poor, you probably eat a lot of foods that are not so good. You probably do a lot of lifestyle things that are not so great. And so, you know, there's a ton of omitted variables here that are probably highly correlated with hot dogs eaten. So when you see these stupid studies, right, of, you know, hot dogs cause cancer, eating dark chocolate reduces cancer rates, that's another one I saw. Well, of course, who tends to eat dark chocolate? Rich people, right? Or richer people. And so, if you're eating dark chocolate, you're probably also doing a lot of other things to take care of yourself. So, all of these kind of studies, you just have to be skeptical about, do you have the right model? What are you missing? And in any empirical study that you find that's published, the authors are asking them these questions. And this is the nature of what I referred to this morning as robustness testing. All of your authors are going to ask these questions of their data. They're going to say, what if I tweak the model in this way? What if I add this variable? What if I take this variable out? What if I do this? What if I do that, right? And what they're trying to convince you of is you could run the model in different ways, but you keep on getting the same result. And that should give you confidence that something important is not being missed, okay? But listen, in economics, any paper, any empirical test, there's going to be somebody that says, well, you didn't include this or you didn't include that, right? And so, this is always going to be a problem in empirical research, right? Is that there's probably always some variable out there that you could include. You have to decide whether the effect is important enough, right? And so the authors are going to try to convince you that other things that they didn't include are not that important. And whether you believe it or not is going to be a big part of whether you think that the study is important and valid, right? And so if you think that there's important things that they miss and they don't talk about it, then you should probably question the results of the study. Very quickly here, I'm hitting my limit of time. Last thing I just wanted to talk about, hopefully this is something that is closer to the forefront of your mind, is hypothesis testing. What can we say about their significance? Once we have alpha hat and beta hat, what can we say about their significance? Meaning, is it important? Is the effect here important or is it not? There's a number of ways that you can do hypothesis testing, and let me just kind of briefly talk about some of the most common ways that you can do hypothesis testing. Once again, some of these papers are going to do many different types of hypothesis testing. Some of them are going to be quite complicated, but all of them will at least use a few of these relatively simple or basic hypothesis tests. One, which is not really technically a hypothesis test, is to look at R squared. The percent of the variation of y that's explained by the model. So as probably most of you know, R squared is a number between 0 and 1. If it's closer to 1, that means that it explains more of y. And if it's closer to 0, it means that you explain less of y. Now, here's the problem with R squared. How high is high enough? And the answer is there's no answer to that. There's no answer. And the problem with R squared, and the reason why economists don't really like R squared, we don't use it very much, is there's no real way of saying high is high enough. So some of your papers, for instance, you might find that R squared is equal to 0.5. Is that a good model? It could be. It could be, right? It's just very hard to say. For some economic questions, an R squared of 0.5 is going to be very, very high. But then there's other economic questions for which an R squared of 0.5 is very, very low. And so, really economists tend to avoid R squared for that reason, right? Is it just doesn't by itself tell you very much. T-statistics are much more widely used, right? And hopefully we remember what a t-statistic is. A t-statistic is just your beta hat divided by the standard error of beta hat. And this is distributed as a t-distribution. Every paper you look at, when they report a beta hat, they will also report either the standard error or the t-statistic. Okay, so everybody will always report this. Remember the rule of thumb. If the absolute value of your t-stat is greater than 2, then you can be 95% confident that beta hat is not equal to 0. In other words, that it's statistically significant. You can be 95% confident that it's statistically significant. That is not equal to 0. T-statistics are closely related to p-values. In fact, oftentimes in most of your papers, when they report a t-statistic, they will also report p-values. So 1 minus the p-value is the exact level of statistical significance. The beta hat is not equal to 0. So it's 1 minus the p-value is the exact level of significance. The beta hat's not equal to 0. So for instance, if the p-value is 0.01, what does that mean? P-value of 0.01 means I can be 99% confident beta hat doesn't equal 0, right? So if the p-value is 0.01, I can be 99% confident that beta hat doesn't equal 0. So obviously a low p-value means more significance. Low p-values mean more significance. Finally, some of your papers will talk about f-statistics. And I'm not going to really get into talking about f-statistics. Let me just tell you what they are for your reference. An f-statistic looks at the significance of multiple beta hats at the same time. So instead of looking at your beta hats one at a time, an f-test or an f-statistic looks at multiple beta hats. Sometimes this is called joint significance. Okay, I'm not going to ask you to know more about f-stats. Your author will report whether they're significant or not. you can just believe your author, right? But when they're talking about F-stats, that's what they're talking about. It's very similar to a t-test or a t-statistic, but with multiple variables at the same time. Okay, one last thing, and then I promise I'll let you go. This is, when we talk about hypothesis testing, this is all about statistical significance, right? Statistical significance. But as economists, I also want us to think about something called economic significance. Is the impact big enough to matter? So when we look at results, we should, and this is one of the things I really encourage you to do in your papers, is when you look at results, put them into economic terms, right? Put them into economic terms. Like, how am I supposed to understand how big the effect is here? How am I supposed to understand how big the effect is here? So, you know, let's say I'm looking at a study that is looking at the impact of education on income levels. And the study finds that, yes, education is significant in explaining income levels. But then you ask the question, well, how significant? In other words, how big is the coefficient? And you find that a year's worth of schooling is worth $100 in income. Well, to me, that's not significant, right? You can have something that's statistically significant, but not be economically significant. And so a lot of bad research, I'll have to say, and not just in economics, but in across disciplines, is not really thinking about the economic or the practical significance of things, right? This is actually a question that the medical research is dealing with. Because oftentimes there'll be these medical studies that say, well, you know, this procedure is statistically significant in extending life. People are like, oh, great, sure, let's do it. Cost $2 million, let's do it. And then you look at the study and you see, yeah, it extends life by an average of 6 weeks. Well, okay, that might be statistically significant, but is extending somebody's life for 6 weeks worth $2 million? That is a different question, right? And in many ways, a more substantial question. And so, you know, listen, I admit this is a hard thing to do. It's so easy to test statistical significance, and as you read through your paper, you're like, oh, this is significant, that's significant, okay. But I do encourage you, particularly for the big results, can you put the size of these results in some sort of practical context for your reader, right? Can you tell them, well, how important is it? If education improves income, how much? How valuable is a year's worth of education, right? Put that in some sort of practical way that the reader can understand. Hopefully your author does that for you. If it's a well-written paper, your author will do that for you. But I can't swear that every paper you're going to be looking at is going to be well-written, right? And so sometimes you got to kind of dig a little bit, right? But I really do, that will be one of the things that I look at, particularly in your first drafts, is when you talk about results, can you put them in some economic significance, right? Like, what is this practically telling us, right? I think, and so I really want to encourage you to think about that as you read these papers. So anyway, that is your charge for this weekend, right? Is to begin to do a little bit of work on your literature review. If you thought about questions, you know, thinking back to some of the things we've talked about this week, you can also look ahead if you want to look in the syllabus and look at some of the topics of things that we're going to talk about next week and the week after. That might give you some ideas too. Or you can send me an email, right, this weekend. If you're thinking about a couple of topics, you don't know if one of them looks good, you know, send me a brief email and I'm happy to give you a little bit of feedback. And then see if you can find a paper or two, that might be interesting. Because remember, on Tuesday afternoon, I'm going to take a little bit of time to meet with each of you individually, and we'll kind of talk about what you're thinking about. If you found any papers, I'll give you some maybe if I have some ideas that you can work on, but we'll have conferences on this Tuesday. So over the weekend, put a little bit of thought into it so that you don't come to the conference with just a blank slate, because that will waste some important time for you. Okay? All right, everybody. Job well done. Have a good weekend, okay? All right, see y'all.